To illustrate the rules of ownership, we need more complex data types than we have seen so far. So we will use a string as an example here and concentrate on the parts of string that relate to ownership. These aspects also apply to the other complex data types provided by the standard library and that you create. So we have already seen string literals. So by string literals, we mean if we write let s equal to and then we assign a hard-coded value to it. So we have seen this case, but these literals are useful and in fact these are efficient. But it's not possible to use these string literals hard-coded always at the compile time because we have to know the exact string that we want to work with. And it's not always the case that we know the exact string at the compile time itself. For example, we may be taking some input from the user and based on that, some string value may be assigned. We will be working on different strings. So we don't know beforehand during the compile time. So we will use a second string type called string. And we will write as let s1 equal to string and then from and then we can write the string. So what will happen here is that this string will be stored in the heap. So it will be requested from the operating system to provide enough memory to store this text. And we can mutate this string also. So let's make it mutable. And this will not be mutable. So we can mutate it using a pushstr function. So here the main reason for using the heap allocation instead of this stack allocation is that we may not be knowing the string always at the compile time. So in order to do that, first we need to request memory from the operating system at runtime. And this we are doing here using this string from. So this will request the memory from the operating system to store this hello. And then after we are done using with the string, we need to return the memory back to the operating system. So returning memory to OS is done in different ways in different languages. For example, in some languages, there is garbage collection where the programmer doesn't have to do anything. The garbage collection algorithm will look for memories that are not reachable and not used and that can be collected. And in some languages where the garbage collection is not there, it's the programmer responsibility to free the memory when they are done using the memory. But this second approach has too many challenges. For example, if we free the memory before some other use of the memory is required, then it will lead to error-prone code. And similarly, if we don't free the memory, then it will be leakage situation. So it's very challenging to pair exactly one allocate with one free. We cannot do free multiple times on the same allocation. That will lead to errors. So it's very challenging. So how it's handled in Rust, it takes a third approach. So these two approaches are not followed in Rust. So here in Rust, memory is automatically returned once the memory variable goes out of scope. For example, here we created a string s and we requested memory from the OS and it was allocated to us in the heap. Then we can do the various stuffs with s, and here with this closing braces, the scope of this variable s ends and we can no longer use the variable s here and the memory is returned back to the OS. So this has a profound impact on the way Rust code is written. So you may be thinking that it's a very simple situation and what's the problem here? But it will become obvious when you see more complex situation where some memory is allocated in the heap and there are multiple variables that are trying to access that memory. So let's see that some of those complex situations. So we will see the interaction between variable and data. So same kind of data, maybe there may be different types of interaction between variables of different type. For example, if we write a variable x and assign a value of 10, and then we create a new variable y and assign it to x, then there is a copy because this is a scalar value and this value is copied, and y also get a value of 10. So when we do println x, then it will print 10. When we do println y, it will also print 10. So it's copied here. But if we see this example, which looks very similar to this, but here there is a difference that this hello is stored in heap instead of a stack. So here also we are creating a variable s1, and this will be holding the value of hello. Then we are creating a new string s2 and assigning it s1. But here it will not be a copy. So what happens here is that s1 will hold three values. One will be pointer, one will be length, and one capacity. So length here is 5 because we have 5 characters here. So length is 5. Capacity is here also 5. Capacity and length are important, but not in this context. And this hello is not stored in the stack. So this part is stored in stack, and hello is stored separately. So HELLO. This can be a very big string also. So this is in the heap, and this is just a pointer to the memory that is allocated in heap. And this is S1, this part, S1. Then we do S2 equal to S1. So what happens is that this stack data is copied here. So capacity, length, these will be copied. And it's a shallow copy. So the pointer is only copied, but not the complete thing that the pointer points to. So this pointer will also point to this memory address. So if this S1 is here and S2 is same as we are assigning to S1 to S2. So when this goes out of scope, then we have seen that it will be automatically returned. The memory will be returned back to the OS. So here both of these are pointing to the same memory in the heap. So it will first S1's memory will be freed, and then S2 will also try to free this memory, hello. So it will be double free and will lead to corruption. So you will think why this is so, why not make a copy here and make this PTR point to, let's copy the heap memory also and create a separate copy. So in this case, there will be too much overhead and it will not be efficient. So this is the way it works here. Both will be pointing to the same address in memory. So now let's see this in the code to verify if this works. So first we will see the simpler case. X is 10, and then we do y is equal to x. And now let's print. First we will print x, then we will print y. And we see that both x and y get the value of 10. So both are valid and we can use both of them. Now let's just illustrate that point also, that once we get out of scope, the memory is freed. So let's create a string s1, and we do string from, and then we do hello, and let's make it mutable. And then we do s1 dot push str, and we append world to it, and now we print, just print s1, and let's run it. So there is an error. Let's try. So we see that world was appended to it. So it was mutated using pushstr. Now let's try to access it outside this, and it will error out saying that S1 is not in this scope. Now let's see this point, that to confirm that it's not a deep copy but a shallow copy, and when we assign S2 equal to S1, then we can no longer use S1. This is called move. So the ownership of this heap memory, earlier it was S1 was owning this. Now when we do S2 equal to S1, now S2 is owning this part of memory, and the ownership has been transferred from S1 to S2, so that when it goes out of scope, it's the responsibility of the owner to free the memory, and it will be freed only once. So you can no longer use S1. So let's see this. So now we do S2 equal to S1, and now we will print. First we will print S2 to see everything is working. So we see that here S1 is the owner. So when we printed, it printed hello world. Then we assigned it to S2 and we printed S2, and it's getting the same string. Now just to confirm that now we cannot use S1 because the ownership has been transferred to S2. Let's print S1 again. And let's see what happens. So we straight away get an error that moved value S1. So S1 has been moved. S1 is no longer owning the heap memory corresponding to this string, hello world, hello and world. So this shows that we are just transferring the ownership. In order to do this kind of thing, that it holds a separate memory in heap, we will do a different approach called clone. So here we saw move. So in order to do deep copy, we can use clone. So that was a brief introduction of how memory allocation works. And then we will continue our discussion on ownership in Rust in the further videos. Thank you.